1. We're Group 2, the wireless hand sensor. I am Mushfiq Sarkar.
I'm Anton Bilbano.
And I'm Jason Yostin.
This presentation will begin by explaining the basics of the wireless hand sensor and where it is applicable. Jason will explain the details of the customer and engineering requirements. Anton will be explaining our block diagram. Finally, we will wrap up the presentation by explaining our project timeline.
Our main goal with this project is to provide the end customer with the ability to control their computer without the use of a mouse. The mouse has been around for decades, but minimal effort has been done to control the computer environment with another alternative. We want to create an alternative where a glove is worn on a person's hand. The glove will be equipped with touch-sensitive buttons to map mouse clicks and various other actions. Rotation of the hand will control the mouse cursor on the computer screen. The reason why we want to pursue this project is threefold. We want to be able to control the computer mouse with the ability to move around freely. We have personally been in situations where the computer is not in our reach in the room, but an action still needs to be performed. With the wireless hand sensor, that action can be accomplished without the need to come close to the computer. The current optical mouse system limits simultaneous use of the mouse and keyboard. Our goal is to provide close to simultaneous use of the keyboard and mouse. Our last goal is to make the system portable with wireless connectivity so it is movable. Next, I will compare the traditional mouse and our project. A project cannot be justifiable in terms of how fascinating it is, but if it has a potential market. There are 3 reasons as to why the wireless hand sensor can be better than the mouse. The device does not require any type of surface. The traditional mouse requires a surface, so the optical sensor can map the coordinates of the mouse to how the surface has changed. Next, our device will be usable across the room. This gives the user freedom to move without being tied in front of the computer. We as humans would be more inclined to use a device that would allow us to perform natural movements. We believe the mouse to be outdated, and as time goes on, technology is becoming portable. Therefore, it is time to make an attempt to producing a product that will provide a more intuitive control of the computer.
Here are a few project requirements which will guide the design and implementation of the wireless hand sensor. Our goal is to provide the end user with a convenient, simple way to control a computer wirelessly. Our glove design incorporates a gyroscope and accelerometer to create an inertial measurement unit, which can sense how tilted a user's hand is by comparing its readings to the gravitational force of the Earth. In order to attain an accurate measurement, we will be taking at least 80 data points per second. This digital information will be sent to the device driver, which will control the mouse pointer on a computer or keyboard macros. The graphical user interface is the way users will talk with the glove in a simple top-level view. Users will be presented with a picture of the device with a drop-down menu for each button. Possible selections include left, right, and middle clicks, maximizing or minimizing a window, or media functionality such as playing or pausing. The GUI will incorporate the option to select the sensitivity level on each axis of rotation, ranging from 1 to 5. Every battery-powered device eventually runs out of power. When the batteries run out, users will be able to connect this sub-circuit, which will charge the batteries completely within 24 hours. One of the main goals of our product is portability. In order to use the device in a variety of settings, wireless data communication will be used so that no wires will tether users to their machines. This will grant the user freedom to move about a room or to even complete non-computer related tasks, seamlessly switching between using and not using the device. Most input devices require some type of feedback to let the user know that they have pressed a button. Computer mice have an audible click. The LED feedback circuit will provide this type of response in under 50 milliseconds. This feature will provide quick response as to what state the glove is in, such as on, off, and calibration states.
The InventSense MPU6000 is a perfect chip for this project because of its integrated accelerometer and gyroscope. We will be using yaw, which is z-axis rotation, along with the pitch, which is the x-axis rotation. Yaw will result in left and right hand rotations, and pitch will be up and down. This will give the intuitive feel to the user, who can act as if they are pointing to where the cursor should go. The two inputs in the block diagram that are of most importance are the environment in and VCC. The VCC of the chip needs to be close to perfect because the accelerometer and gyroscope values that are sent to the microcontroller map according to the VCC. For a few milliseconds after the chip is active, a stable point is established and all future points subtract from the stable point. This takes away the gravitational effect of the system. Our IMU is accurate, and this will help us further develop the wireless hand sensor.
Here we have a top-level diagram for our device, the wireless hand sensor. In this diagram, you can see how the device is broken down into individual blocks. There are 8 blocks total. The first one is the power block. Then we have the controller block, transmitter, receiver. Then next we have the inertial measurement unit, the sensor block, the feedback block, finally the computer block. Next I'll break down what each block is made up of, and also what are the inputs and outputs going to each block. Let's start with the power block. This block has one output signal, and that is simply the raw power output from the battery. We'll save the microcontroller for last. Let's start with the IMU, or the inertial measurement unit. The IMU and the microcontroller communicate using the I2C protocol. The first wire, known as the SCL wire, is basically a clock. On the positive edges of the clock line, the SDA line, or the data line, will be red. Now we have the inputs to the IMU. Here we have the environment input, the user input, the VCC input, and the ground input. VCC and ground are simply the VCC and ground connections on the microcontroller. Next is the user input. This is the motion of the hand, which the IMU will pick up. Now we'll go over the touch sensor block. Included in this block are all of our touch sensors as well as the conductive fabric connections. Inside this block is also a multiplexer. We use a multiplexer in order to turn 8 analog inputs into only 1. This of course comes at the cost of 4 of our digital outputs. Here you can see the user input. Again, this is the touch sensors and the conductive fabric connections. Here we have VCC and ground again, which are just connected to the VCC and ground pins of the microcontroller. Over here we have the MUX select line, which is really 4 wires. 1 wire is used as an enable, and the other 3 wires are to cycle between the values of 0 and 7. Above that is the touch data signal. This goes to one of our analog inputs. When we cycle through 0 through 7, we are checking the status of this line to see if one of the touch sensors is pressed. The next block I'll go over is the feedback block. Here we use the shift register to control 8 LEDs. There is a clock line and a data line. On the clock, we output a 1 or a 0 on the data line to set the state of an LED. Here's the LED feedback line, which you might recognize from the basic block level diagram. Here we have VCC and ground, which again simply go to the pins of the microcontroller. Next, I'll go over the transmitter block. Here we use an XBee Wi-Fi transmitter. The XBee needs a 5-volt VCC line. Now let's talk about the microcontroller. The microcontroller that we use is called an Arduino Pro Mini. It operates at 5 volts and has 4 analog inputs and 14 digital outputs. At 5 volts, it operates at 16 megahertz. All of the blocks that I've talked about so far are within our glove enclosure. Now let's go outside the glove enclosure. Here you see we have the receiver and the computer blocks. The receiver block simply communicates with the transmitter over Wi-Fi. It's powered by USB. Between the receiver and the computer are 2 lines, the computer data in and computer data out. Next we have the computer block. With the computer we will be controlling the mouse pointer as well as executing some shortcuts for the user. The code block going into the computer will be a driver which allows our device to communicate with the computer. We will send data to an application specifically for our device.
Here we have a rough project timeline. After designing each block, we will put them all together by week 3 of winter term, allowing ample time to test, redesign, and build the final product.
The wireless hand sensor is going to be an amazing device. Currently, there is very minimal development in this area, which allows us the opportunity to create a brand new product.
To accomplish this, data will be gathered with an inertial measurement unit
processed with a microcontroller, and wirelessly transmitted to a computer, all while the button functions are controlled by a graphical user interface.
Thanks for watching, and please stay tuned for future updates regarding our device, the wireless hand sensor.